change in x. Can everyone see my screen? Is there anyone who still can't see my screen? Please let me know in chat, or you can go ahead and unmute yourself. Great. So our change in y over change in x, the change in y is 4 over 1 in the first case, is 8 over 2 in the second case, and is 8 over 3 in the third case. Of course, those first two cases both reduce to 4. My screen would stay in its spot, 4 and 4, but this reduces to 2.6 repeating. Obviously, 4 equals 4, but 4 does not equal 2.6 repeating. So since those slopes are not constant, this is not linear. Slopes are not constant. So that one's not linear. Moving to the next one, if we check our changes in x, the first set increases by 2, and then by 1, and then by 1, and then by 2. The y's, first set is going to increase by 6, and then by 3, and then by 3, and then by 6 again. But again, we don't care that those numbers in themselves are matching. We care that the change in y over change in x is the same. So in this case, we're comparing 6 over 2 to 3 over 1 to 3 over 1 to 6 over 2. All of those reduce to 3. So the slope is constant. So we have a linear equation. We can go ahead and actually find the equation on the line. So since we need y equals mx plus b, I have my m value. I just found it. Why is that erasing? I just found my m value of 3. So I don't actually have to go about and find it again. I can just use it. Now I have to pick whichever one of these points makes me happier. I'm going to choose 4, 0. And then we're going to go ahead and plug that into y equals mx plus b. So the y is 2, m is 3, x is 4, n plus b. You get 2 equals 12 plus b. Subtract 12 from both sides. You get negative 10 equals b. So then you have your equation is y equals 3x minus 10. Questions, concerns? Great. Then we're going to move on to 1.3 notes. Pull those up again. Now, of course, we frantically started this last time. Now, for the sake of time, seeing as how my last class went, can everyone see this? Does anyone not see the notes on their screen?
I can see the notes.
Thank you.
We can see the notes.
At any time, if it freezes, if it lags, just let me know in chat. So we skipped these two examples here. Because my last class, I went over them and then barely had enough time to get through the rest of the stuff we needed to go through, I'm going to continue to skip them. I will put the completely completed notes up on Blackboard if you wish to look at them. They are just other examples of average rates of change. Average rates of change. So you're just using the average rate of change idea on these two examples. So if you'd like to see them, they'll be up on Blackboard. We are going to do another average rate of change example, just not these two specific ones. So a reminder, we talked about the average rate of change, which was our f of b minus f of al over b minus a, which is suspiciously like slope because it is a slope. So we also talked about how the verbiage average velocity is exactly average rate of change, just in the specific situation of a distance function. So let's go ahead and start here at example 4. So consider the following table, which shows the height of a grapefruit above the ground t seconds after it is thrown. Okay. First thing we're going to want to do is we're going to want to find the change and then the average rate of change. And those are two completely different things. So the change and then the average rate of change of the height of the grapefruit, the first 3 seconds give units and interpret your answer. So what the first 3 seconds is going to tell me is going to tell me I'm looking between t equals 0 and t equals 3. Okay. So I'm looking at this data set here. in this data set here. Now, when it says change, that's just literally asking for what is the change in height between those two values? How much did it change in that time? So if we're looking for the change in height, we're going to take our height at t equals 3, which is 162, the ending height, and subtract the height that we started with, which is 6. So we're going to end up with 156 feet. And what that's going to tell us is that's going to tell us that the grapefruit goes up 156 feet in that time frame.
I ate grapefruits.
Okay. It started at 6, it ended at 162, so it moved 156 feet. Okay. Questions about that? I don't think what was just said was a question, but I also barely heard it. Average rate of change. So that's our slope idea, f of b minus f of a all over b minus a. We're still using the same two data points. So we have 162 minus 6 over 3 minus 0, which is going to give us 156 over 3, which reduces to 52 feet per second. And now we want to interpret that. So I'm going to scroll back up really quick. We'll be back down in a second. So remember what we said on Fridays, this is not telling us that it's constant over that time interval. It's telling us on average what is happening. So that's how we're going to think about our interpretations for the average rate of change. Now you could also interpret it in terms of a slope because it is a slope. But especially in the context of velocity, it's much easier to just think about it as on average you're traveling at this velocity. So how we would say this is we would say, or I would say how I would phrase it would be during the first 3 seconds, the grapefruit is traveling, and I, for some reason, can't remember if it's 1 L's or 2, but I'm a math person, not an English person. So traveling at 52 feet per second on average. You could say traveling on average at 52 feet per second. Again, as long as it gets the point across, I don't really care. But the main thing is that you do kind of want that language on average in there to get the point across that this is not telling you exactly what's happening, but is telling you kind of on average what's happening in that time frame. All right, part 2, find the average velocity. So same idea, just different words. We're still finding the average rate of change of the grapefruit over the interval t equals 4 to t equals 6, and explain the sign of the answer. So now we're using 2 different data sets. We're using 4 and 6, but still average rate of change, same idea, change in y over change in x. So 150 minus 30 over 4 minus 6. So, sorry, negative's going to be in the denominator. 120 over negative 2. So negative 60 feet per second. Now, why is it negative here? If you're used to physics, you probably already know. If you haven't really taken a physics class, you might not know. So whenever we're talking about velocity, we also need to know what direction we're traveling in. So in this case, since we're throwing the grapefruit up in the air, we're going to count any traveling upwards to be in positive velocity, and therefore, if it's going to be traveling downwards, it's going to have a negative velocity. So essentially, this negative is telling us that it's traveling downwards. So the negative means it's traveling, and I'm spelling around again. Now, in most cases, because I know I don't believe on this homework, but in future homeworks, there are some velocity-based questions where you do need to consider, is the velocity positive, is the velocity negative, to figure out which direction you're traveling in. They should specify, you know, positive velocity is traveling to the right, where positive velocity is traveling towards home is usually how the context goes. So they should tell you in context what positive velocity means, which then you can then extrapolate what negative velocity would mean. But essentially the signs of velocity are just telling us which direction it's traveling in. Questions on that, either of those pieces, that example. All right. Next one. A car travels away from home on a straight road. Its distance from home at time t is shown in the following figure. Is the car's average velocity greater during the first hour or the second hour? So first thing I'm going to do is I'm going to split this up between the first and the second hour. So the first hour would, of course, between 0 and 1, and the second hour would, of course, between 1 and 2. So if I wanted to compare these average velocities, the best way I could do that would be to compare numbers, but I don't have any y values here, so I'm not going to be able to actually calculate them. So how are we actually going to be able to compare these? Well, that goes back to the idea. Again, scrolling up to remind us because it was on Friday, although it's lagging, so we'll give it a second. There we go. So remember, this average rate of change does tell us about slopes. So if we consider the line between the points that we care about and we look at their slopes, we'll be able to compare that. So we don't actually need a number. We can just kind of look at the lines that we're working with. So if I go between 0 and 1 and to the very best of my ability, draw the line between them, and then I go between 1 and 2, and to the very best of my ability, draw the line between them, which matches very nicely to the actual function. But now I'm going to compare those two line segments. So which line segment has a larger slope? Well, this first one is much steeper than the second one. So the first one is steeper, and then the other one kind of starts to level out a little bit. So we're going to say that the average rate of change is greater in the first hour. And let me write a little tiny explanation so that you can kind of remember if you're looking back at this later. We can tell because the slope of the line between 0 and 1 is greater than that of the line between 1 and 2. Can't spell. So even though we had no numbers to compare here, since we know that the average rate of change tells us about a slope, we can just compare the two slopes of the little line segments, and we can still figure out which one's greater. Savvy? Questions? All right. Any questions about average rate of change? Because I'm going to move on to a completely different concept. Going once. All right. So the graph of a function is going to be called concave up if it bends upwards as we move from left to right, and the graph of a function is concave down if it moves downward as we move from left to right. Now I'm about to draw some pictures to try to demonstrate that. A line, a straight line, a linear line, is neither concave up nor concave down. It has no concavity at all. So we kind of have two options, this or that. So this is concave up, and this is concave down. And in each one of these two, so in each option, there's also kind of two options in themselves. One piece that's decreasing and one piece that's increasing. Same thing with concave down. This piece is increasing. This piece is decreasing. Okay. Now, thinking about these in general, one of the directions is kind of harder to think of intuitively than the other direction. So if you look at concave up, I think this piece on the right, it kind of makes sense that that's bending upwards over time, right? Just it's continuing to kind of increase and it's getting larger, right? Whereas this side, the other side, it might be a bit more confusing as to why that's bending upward. But if you think about it, pretend you're like flying an airplane or a helicopter, and this parabola is mapping, where your helicopter is. So say your helicopter is going downwards towards the ground and you're trying not to crash it. So you're trying to make the helicopter kind of pull up in a way, but the helicopter isn't going to magically change directions in an instant. It kind of has to slow down before it can start actually heading back upwards again. So that's why this side of the concave up is still considered bending upwards, because it's bending upwards. I don't know how else to say it, but hopefully that makes a little bit of sense. And then on the other side, again, this right side, I think it makes sense that it's bending downwards. But this right side, again, imagine you're in the helicopter and instead of going up, you want to go downwards. Well, you have to slow down eventually. If you're trying to make it go down, you have to slow down before you can go downwards. So this is still bending downwards. It just kind of has to reach its peak before it can head down, if that makes any sense. An easier way to figure it out, if that was way too confusing, is a lot of people will always say concave up like a cup and concave down like a frown. It's kind of silly, but it can kind of just make you remember the two pieces. And then once you can just like draw out the pieces on your piece of paper, concave up like a cup, concave down like a frown, and then just use them. So let's see how that's going to work. So use the following figure, estimate the intervals on which the function is increasing or decreasing, so things we already know how to do, and then concave up and concave down, so the new pieces. So first, let's look at increasing and decreasing. Also, while I'm thinking about it, your quiz, I have them graded, I just haven't put them into Blackboard yet. That's what I'm going to do before the end of the day today. So your grades for the first quiz will be in Blackboard by the end of the day. If you are in class on Wednesday, you'll get them back on Wednesday. If you're not going to be able to be in class on Wednesday and you really want to see the quiz and anything I wrote down on it, email me and I can scan it to you. That might not be instant, it might take me some time to get around to it, but send me an email and eventually I will get that out to you if you want it.
Were they good? Were they good?
I'm sorry, was that actually? I'm sorry?
Were they good? Were the quiz
Were
grades
they
good?
good? I'm fanning through them right in front of my face. They were pretty good. They weren't too bad. I wasn't mad at them in any way, shape, or form. There was a few of them that definitely, be careful to read my instructions. There were some pieces where I asked you to, explain why they were not a function, and some people missed that piece of the instructions. So that was, of course, kind of iffy, but for the most part, they weren't bad. No. All right, back to this example. So increasing, decreasing. So we're going to split this up, where it kind of changes from going up to going down. So we're going to say 2, and this is kind of past 6, but let's just say 6 for ease. So let's assume this is going downwards and upwards forever, so we're going to use infinities. So that first piece from negative infinity to 2 is going to be increasing. That 2 to 6 is decreasing. And 6 to infinity is increasing. So I breezed through that because that's supposed to be the review, but let me know if you have any questions. Please don't hesitate to stop me if I ever go through something too fast. But now we want to look at this new idea of concave up and concave down. Now, this idea is a lot harder to see at first, especially it's very hard to see where it changes. So a lot of times that's why you're going to see estimate, because we're just going to get a general idea for where it's going to change. In a couple chapters, we're going to have a, kind of calculus-y algebraic way to find where it changes. But for right now, we're just kind of going to have to guess. But the way I like to go about these, especially if you're not used to doing these, I think one of the easiest things to try to do first is to locate pieces that look like this, that look like the concave up and concave down pieces. So if I'm looking at this, well, I have this spot right here. It definitely looks like that piece a little bit. And then I have this piece down here. that, kind of looks like that piece, right? So if I kind of pull those out and say, okay, well, I have this piece and this piece that look definitely concave up and definitely concave down. I have those backwards. But if you pick out the pieces that are definitely one or the other, then that's a great starting place. Now, those are the only two pieces of my graph that are definitely one or the other. Everything else is, kind of just a generic straight line. I don't see anything else that kind of looks like this. Maybe I should have said straight line, but there's nothing else that looks like that, right? So I have these two little boxes on there now. And so however many boxes you find, and you don't actually have to box them, however many things you find that look like those pieces, those are going to be how many intervals you have. So here we're only going to have 2 intervals, okay? Now this first piece around 1 to 3, that's concave down, right? So that piece in there is definitely down, and this piece in here is definitely up. So those two kind of pieces I have figured out, but what about the rest of it? So again, the only time they're going to change is if you find places that look like this. So we know that they're not going to change anymore. So essentially from this box down to the left, that's going to continue being concave down to the left. And this is going to be continuing to be concave up to the right. Hopefully that makes sense, because of the fact that we don't find any of these changing points again. So the real ambiguity is, well, what the heck is happening in here? And that's kind of where the estimation comes in. We're not exactly sure where it changes, but somewhere in here, it's got to change from concave up to concave down. So let's go ahead that it changes, say it changes probably about right here, probably at about 4. That's a good kind of like halfway between that peak and that valley, right? So we're going to say that it changes at about 4. So that means that we're going to have a concave down piece from -infinity to 4, that whole entire kind of left side, and concave up from 4 to infinity. And just like with the increasing, decreasing pieces, you could totally add brackets to these. Just like it doesn't make sense to say a function is increasing, decreasing, or constant at a single point, it also doesn't make sense to say concave up or concave down at a single point. It has to be over an interval. So I always kind of default to parentheses, but whatever floats your boat. Savvy? So hold on a second if there's any questions in chat, and then we'll go on to the next one. All right. From the following table, does f of t seem to be increasing or decreasing? Do you think the graph would be concave up or concave down? So, increasing or decreasing, is it going up or is it going down? Now that's always kind of considering the y values. Are the y values getting larger or the y values getting smaller? Well, what's happening here? If we look at these y values, as we go from left to right, those are getting larger over time, right? So 12.6 is less than 13.1 and so on and so forth. So since the y values are increasing, f of t is increasing. If the y values were getting smaller, f of t would therefore be decreasing. But now, well, what about concave up and concave down? And that's again where it gets a bit more harder to see, and we have to do a bit more work here. Let me start looking at the slopes. So let me try to find, just like we were doing in the warm-up, let me find kind of our change in x's and our change in y's. Well, change in t's, I guess. But anyway, all of these are increasing by 5, so that's super nice. And then the f of t values, well, the first one increases by 0.5. And then the second to third one increases by 1, and then 2.1, and then 3.8, and then 9.6, and then 13.1. Okay. And technically what I want to look at here are the slopes, which I can't spell. That's not how you spell slope. Slopes. So again, just make sure we're getting it. Change from y over change in x. So technically change in f of t over change in t. So 0.5 over 5, 1 over 5, 2.1 over 5, 3.8 over 5, and so on and so forth. 9.6 over 5, 13.1 over 5. The nice thing about this example is that all the change in t-values were the same. So we kind of don't have to figure out what the actual values are because the denominators are the same, so we really only have to care about the numerators. But if all the denominators were different, you would just punch this into a calculator and compare the actual decimal values. But here, since the denominators are all the same, let me go ahead and look at the numerators. Well, the numerators are increasing, right? Those values are getting larger. So since slopes are increasing, that's the thing you care about for concavity. Are slopes increasing or decreasing? So since slopes are increasing, this is going to be concave up. So in a different color, let me write this down because it's more of a generic note than this actual example. Oh my God, go away. So slopes are increasing as concave up. And so then slopes are decreasing with being concave down. So if you're ever given a table and you want to know about concavity, the first thing you need to get are the actual slopes. And then you need to compare the slopes. Are the slopes getting larger or are they getting smaller? And that can tell you whether or not it's concave up or concave down in whatever piece you're looking at. Make sense? Questions, concerns?
No.
Okay. All right, not seeing anything in chat, so we'll move on. To the last idea
Can
that
you
we
go up
need.
for just a second? Sorry.
Yeah, no, you're fine.
All right, I'm good. Thank you.
So we've got one more idea we've got to talk about for 1.3. Change back black. So what if I asked you if a population change of 1,000 people would be noticeable? Well, it would kind of depend on where you are. Say you're in New Mexico in a city called Coyote, and that had 128 people in 2017. Now I know 2017 was a couple of years ago, but just pretend it's 2017, and all of a sudden 1,000 people move in. Those people are going to notice because they only started with 128, and all of a sudden they've got 1,000 more people. But say you're in New York City that had 8.5 million in 2017, and actually 1,000 people move in, not many people are going to notice at all because it's just an obnoxious amount of people already. So we kind of want to be able to compare, not really compare the two, but to kind of figure out how large or small a change is from starting value to an ending value. So we have this idea when our quantity P changes from P0 to P1, we define the relative change to be the following. It's going to be the change in P over P0. Or if you prefer, P sub 1 minus P sub 0, or P0 over P0. So the ending value minus the beginning value over the beginning value. Okay, so maybe some people like to write it like there. Whoops, and I'm writing it wrong already. So the ending value minus the beginning value over the beginning value. That's the not really mathy way to put it, but if it helps, go ahead. Now the relative change is usually a number without units, which is super nice. And it's also often expressed as a percent. So you will calculate a decimal, and then usually you'll change it to a percent for the actual answer. In terms of Wiley, just kind of be careful. Read usually puts a percent symbol after the blank if it wants the percent. So just kind of be careful there because sometimes they do actually want the decimal value. So just kind of look to see if they're saying percent. It might say percent before the blank in words, or it might have a percent symbol after the blank in symbols. So let's look back at that idea of this population change in New Mexico versus New York City. So I'm going to be calculating two relative changes. So let me break that up. So say I'm looking at the city in New Mexico first. So that started at 128 people. right? And then it changed 1,000 people moved in, so now they're at 1,128 people. So if I wanted to calculate the relative change there, well, this is my starting value and this is my ending value. So I've got 1,128 minus 128 all over 128. So of course that reduces to 1,000 over 128, which is 7.8125 as a decimal. So again, this would be the decimal answer that we get. But then also, often we would want to change this to a percent. If you forget how to change something to a percent, you take the decimal and move it 2 spots over to the right. So that would mean as a percent, this would be 781.25%, which is why it's such a noticeable, obnoxiously large change, because their population just changed by 781%. Okay, so that's kind of what this is showing us, is how much did we increase from one to the next? What was the percent increase? Well, from 128 to 1,128, it's a 781.25% increase. Whereas if we're in New York City, well, of course, now I got to write 8 million out numbers. So 8.5 million, sorry, was their starting value. And then a measly 1,000 people moved in. So we started with 8.5 and ended with 8.5 plus those, if you will. So if we calculate our relative change here, we have our ending value minus our starting value divided by the starting value. Oh, so many zeros. I trust and believe we can type that into a calculator. So 1,000 over 8.5 million. Now there's too many zeros in that one. Oopsies. Now, as a decimal, this is 0.001176475. And the 5 is lagging. There it is. Let me just, whoops. Kind of cut that off. No, we'll just take the whole thing. Never mind, I already wrote it all out. So as a decimal, if I move that 2 spaces over to the right, I'm going to have 0.0176 blah, 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 blah %. So that's kind of, obviously showing us that, yeah, no one's going to notice because it's not even, it's like barely 0.02 of a percent. So that change compared to the change in New Mexico, obviously kind of depended on how much you started with. Questions on that? All right. Okay. So let's do a few more examples of relative change. So find the relative change in price for the following items if the price increased $2. So we're always going to take whatever we started with and increase by 2. So the first one, a gallon of gas costing $2.25. So if the starting value was $2.25, then the ending value is $4.25 because we're saying that we're increasing by 2. So our relative change, 4.25 minus the beginning value of 2.25, all divided by the beginning value of 2.25. So 2 divided by 2.25 is 0.8 repeating. So let's just say 0.889 for the sake of changing it over to a percent. So that would become 88.9%. And again, because I haven't reiterated this again, the decimal doesn't have units. Okay, so the nice thing is you don't have to worry about units here. There's no units on that decimal. So that means that the cost of gas increased by 88.9%. Well, okay, part 2, what about a cell phone costing $180? Well, that's our starting value. Our ending value would then therefore be 182. So it's not as much of a difference, so it's probably going to be a much smaller percent. So we've got our ending value minus our beginning value divided by our beginning value. So we've got 2.
Wait, where are you getting 182 from?
Yeah, so again, we're increasing everything by $2. So if it started at 180,
Gotcha.
increasing by 2 is 182. So we've got 2 over 180. This would be 0.01 repeating. So let's just say 111 for the sake of converting to a decimal, which would be, so move this over 2 spaces, 1.11%. Okay. So wait a few seconds to see if there's questions. All right. I'd like you guys to try these last 2 examples on your own. I'm going to give you 4 minutes. At 1:55, we'll talk about them. One thing I'll say about example 11 is you're talking about finding the relative change in the amount sold. The starting value is the 25, and then the other value. It's less clear in the wording there. But I'm going to sit here in awkward silence for 4 minutes while you guys try those 2, and then we'll go over them really quickly before the end of class. Must be 1 second. All right. So let's go over these really quick. So a pair of jeans is originally, so that's telling us that that's our original value. $75.99 is on sale, so our ending value here is going to be $52.99. So our relative change, ending value minus beginning value divided by beginning value. Should get negative 23 over 75.99, which is negative 0.303. So a 30.3% decrease. And that's how I'll write it so that I don't have to write the negative. I could write negative 30.3%. That's another thing with Wiley, is that sometimes they'll have you quote unquote interpret the relative change. And so if it's a negative decimal, it will be a decrease. And if it's a positive decimal, it'll be an increase. So then same prices, but now we're looking at the amount of jeans sold per week. So when it's originally priced, so they originally sell 25 pairs a week, and then they go up to 45 pairs a week. So our relative change there is 45 minus 25 over 25. So 20 over 25, so 0.8. So an increase of 80%. And that's relative change. It's quote unquote simple, but a lot of times the main thing is that people will mix up, especially which number goes in the denominator. So that's why I was saying end minus beginning over beginning, because I think while less mathy, that's a bit more easy to remember, but whatever works for you is best. So that's the end of that. I'm going to talk about, tell you what you're on. Oh my Lord, my English is breaking just in time, I guess. What's going to be on your quiz on Wednesday, and I will type it in chat so that you guys can find it. Yes, so once again, I am sorry that 1.3 was still on your homework. As I said on Friday, I usually try to end things for the homework on Friday, but this stuff is on your homework that's due tonight. So you have your first homework due tonight at 11:59 p.m. Your second homework has already appeared just because they're set to appear on Mondays. So there's this 1 day of overlap, but of course you don't have to do them at the same time. But just remember that the first one is due today, the homework one, the 1-1 to 1-3. So your quiz on Wednesday, and I'll type it in chat so you can find it later. So quiz on Wednesday. It's going to cover stuff from 1.2, so that's going to be linear versus nonlinear. So essentially kind of like the homework, and the warm-up, writing linear equations, which is also part of the warm-up today. And then from 1.3, the main thing I'm going to pull is average rate of change. So those two ideas are going to be on your quiz on Wednesday. So again, the